So in this video we're going to have a look at a selection of circle theorem questions. Now I'm going to run this ever so slightly differently. I'm going to run through quite a lot of questions here. So what I would suggest is obviously having a go, make sure you've watched the previous video on all the circle theorems, see if you can apply any of that knowledge, see how far you can get with each question, and then obviously watch me go through like the explanation of all of these different questions. Now I'm going to run through about 5 questions of just sort of what I would call slightly easier questions, and then I'm going to have a look at 3 specific or relevant exam questions towards the end as well. So we're going to get kick-started with this question, but obviously if you want to try and draw this out and make some notes and have a go, you can just obviously pause the video at the start of each question and then run through the example with me. So this question here, and there's normally quite a lot of language, I've tried to reduce the language as much as possible, but it says BOD is the diameter of the circle, so that's obviously this line just here, B to O to D is the diameter. It says BC and AC are tangents to the circle, and we want to work out the size of angle DOA. So DOA, let's have a look, that is here. So we're trying to work out this one if I label that with an X. And it says you must give reasons. Now for these questions I'm not going to be writing down the reasons, but we will sort of speak about the reasons as we go along. Obviously the bits that you do need to make sure that you're writing down within an exam. Okay, so have a look at this question now. Let's see where we can go with it. Now it says BOD is a diameter, and normally when there's a diameter given we're looking for a right angle somewhere, but this is actually not the case in this question, which is quite interesting. That is actually more just telling us that that's a straight line, I think, because there's no triangle being made via that diameter within that semicircle. So I think that's kind of given us a hint there that there's a straight line going on, and we're going to have to use that at some point. But if we have a look, we have got tangents involved and they are meeting the radius. So we've got some 90-degree angles here that we can draw on straight away and obviously see if that helps us actually moving forward. Now just looking at that, now we've got a triangle here. I'm just going to highlight that. We've got a triangle here where we've got one missing angle. So we can work out that other angle in the triangle, and that's what these sort of circle theorem questions are all about. So just forget about what you're looking for a minute and just see what you can find. So actually looking at that question there, if we do 180 degrees, take away the 90 and the 34, or obviously starting that off we could do 90 plus 34, which gives us 124, and take that away from 180. So 180, take away 124, that's not 124, there we go, take away 124, leaves us with 56 degrees. So that's going to be 56 just there, there we go. And actually, what we've got is 2 tangents meeting at equal length there as well. So these are going to be at equal length, which actually means that that length O to C splits that angle there in half at the end. So this is also 34, and this is also 56. There we go, so actually looking at that now, if I highlight that, we've got 3 angles on a straight line. We've got the X, we've got the 56, and we've got the other 56, making a straight line there. So if we add together those 2 56s, so 56 plus 56, that gives us a total of 112. And if we take that away from the 180 for the straight line, so 180 minus 112 gives us our final answer here. What is it? 68 degrees. There we go. So 68 degrees would be our final answer. Now obviously there's a couple of reasons that we would have given along the route there that I sort of mentioned as we were going. We had tangent to a radius at 90 degrees, obviously giving us our first right angles. We've got 2 tangents meeting at equal lengths, and that obviously forms that little angle bisector there that would give us 34 and 34. And then we had angles on a straight line to finish it off. So there we go. We'd write all those reasons down along with it, but let's have a look at our next question. Okay, so this question says work out the size of angle ADC, and you must give your reasons. Now ADC is this angle just here, and we'll highlight that, we'll put a little X in there. Now what we've got, if we sort of ignore that line CD and AD, is we've got that sort of arrowhead, or if we've got this angle at the centre here made via A and C, and we've also got this angle at the circumference made over there. So we've got a little arrowhead sort of circle theorem going on, and actually you can also see that there's a quadrilateral formed inside the circle there, so we've got a cyclic quadrilateral going on as well. Now first things first, we can just find this angle here because we've got the 168, so we can halve that for this angle, and that would be 84 degrees. Okay, and that is obviously, you've got your angles at the centre, angles at the circumference. Let's get rid of that. There we go, what was that, 80? Let's just get rid of all of that and rewrite it without that arrow. Get rid of this highlighter. There we go, so that'd be 84 degrees. There we go, angles at the centre being double angles at the circumference there. Now we can have a look at this in terms of a cyclic quadrilateral, because these 2 are opposite angles within that cyclic quadrilateral, so we can actually just obviously take that away from 180, as these opposite angles are supplementary, they add up to 180. So take away 84, and that leaves us with 96. And there we go, our reason for that would be angles in a cyclic quadrilateral add up to 180, and there's our final answer. There are different ways of doing this, and to be honest with a lot of these questions, there are more than one way of actually solving these problems, but there's just one way, and obviously you might find your own way of doing that, and that's absolutely fine, but I'm not going to talk through all the different ways. I'm just going to go through the first way that sort of pops into my head as I'm doing them. Okay, so there's one question. Let's have a look at our next one. Okay, so this question says AP and BP are tangents to the circle. Work out the size of angle X, and you must give your reasons. So straight away, obviously it's mentioned that there's tangents, so we know that there's some right angles. So we've got a right angle here, which is made up of those two different angles, and we've got a right angle down here, which is made up of that angle X and the other little angle within this triangle. We've also, again, got tangents meeting at equal lengths, so we've got this sort of idea here, which means that obviously that triangle there, APB, is an isosceles triangle. And if it is an isosceles triangle, then we can work out the two base angles. So if I switch colours, we can work out this angle here and this angle here just by using isosceles triangle rules. And obviously, and to be honest, these isosceles triangles are going to be very, very relevant in these circle theorems. We're going to see a lot of isosceles triangles throughout different questions. So I would actually always be looking for isosceles triangles, and I think we're going to have more than one in this question, but we'll see where we get to. So if we take away 86 from 180, so 180, take away the 86, that leaves us with 94 degrees. And obviously that's going to be split between two base angles in the isosceles. So if we divide that by 2, so 94 divided by 2 gives us 47. So we've got 47 degrees. That's going to go in both our base angles here, 47 and 47. And always make sure you just label that all over the diagram. And now we should actually be able to find the size of angle X straight away there, because these two angles that are made up, we've got the 47 and the X, those two are going to add up to 90, obviously because there's a tangent to the radius there. So to finish that off for angle X here, we can just do 90, take away 47, and that leaves us with 43 degrees. There we go, 43. Right, there we go. So that's our final answer for that one. We could actually be and look at different angles. I'm just trying to think if we could have done that in a slightly different way, because obviously something that I noticed straight away was that we had another isosceles triangle here, this one here, because that length O to A and O to B are both the radius, so that was also an isosceles. So there's probably another way of actually going about solving this, but I think that's quite a nice easy way, forming that isosceles in the first triangle and then just taking that base angle there away from 90. So our reasons were tangent to a radius meeting at 90, and also we had two tangents meeting at equal length as well as isosceles base angles being equal. But there we go, there's an answer to that one. Let's have a look at our next question. Okay, so this question says ABC is a tangent to the circle. BE is the diameter of the circle. Let's just highlight that. So B to E is the diameter. And work out the size of angle ABD and DEB. So we've got two questions within this one, and it says you must give reasons again. So let's start with ABD. Where's that? ABD is just here, and that should be nice and easy for us to do there, because that's where that tangent meets the radius. So if the tangent meets the radius there, the total angle here is 90. So we can do 90, take away that 35. That's going to tell us what's left over. So 90 take away 35 is 55 degrees. And there we go, there's our final answer for that first part. So 55 degrees. Let's just highlight that. There we go. Now the next one is asking us to find out the size of DEB. So DEB is this angle over here. So we can find out the size of that as well. There's a couple of ways that we can go about this actually. Let's have a look. There's two ways. We could get it in one step, or we could get it in two. Now what we have got is we've got this semicircle angle. So we've got this angle here being 90, because angles in a semicircle equal 90 at the circumference. So we can do that, and we can add them together and take it away from 180, and it'll tell us the size of this angle here. But actually we've also got our alternate segment theorem that we could use in this one as well. If you have a look, as we walk through this angle and go up the line, there we go, it's here, so it's equal. So we've got our alternate angles. Oh, I've got rid of my arrow there. We've got alternate segment theorem saying that angle there is also 55 degrees as well. There we go, so we could use two different rules here. So we can use angles in a semicircle adding up to 90, or we could have a look at our alternate segment theorem rule there to say that that one's 55. So a couple of different ways to approach that. That one's a little bit quicker there, only requires one step rather than two, but both ways are absolutely fine. Let's have a look at another question. Okay, so this one looks a little bit more complicated. We've got ATB as a tangent to the circle. Calculate the size of angle OTQ, and you must give your reasons. Now, OTQ is this angle just here, so it's this little angle in between. Now, we've got these lines on this triangle here telling us that it's an isosceles, that they must be the same length. And we know we've got a tangent, so we've got a 90-degree angle just here. And have we got anything else? Nothing else that stands out to me at the moment. So let's just have a look at what we can find. So in between the 58 and the radius there, we can obviously find that out. So this angle here, so we can do 90, take away 58, as obviously tangent meets a radius at 90. So 90 minus 58, and what does that leave us with? 32 degrees. There we go. So that angle there is 32, and we can draw that in. There we go. Now there's nothing really that massively stands out that you can actually go for on this next movement now. Now obviously there are a couple of ways of doing this. I've just spotted two little things. We could draw another line in here and perhaps make a little isosceles triangle. But I'm just thinking, are there any other circle theorems that we can look for? Now we haven't got a diameter. We haven't got any angles in the same segment. We've not got our little angles at the centre or angles at the circumference circle theorem, but we have got like a cyclic triangle here for meeting a tangent, so we can actually apply our alternate segment theorem again. So actually if I go through this angle, this 58, and I go up the length of the triangle, it makes this angle here, so that there is going to be equal to the 58, so this angle here is going to be 58. Again, there's our alternate segment theorem. Now looking at that, obviously we've got an isosceles triangle, and we know base angles in an isosceles are equal. So if we work out the size of these two base angles here, we can do 180, take away 58, and that would leave us with 122 degrees. There we go, 122. Now that is needing to be split in half, obviously because it's two base angles. So if we divide that by 2, that would give us 61 degrees. So both the base angles in this isosceles are 61. There we go, I can just about label that one there as 61. There we go. And now looking at this value of x, look, we know that part of that angle is 32 and the full angle there is 61. So that little value of x must be what makes 32 up to 61. So we can finish this off by doing 61, taking away 32. And what does that leave us with? That leaves us with 29 degrees. There we go. So 29 degrees would be our final answer for that one. There we go. A couple of different ways that we could have approached that. Actually, I think you could have also done a little bit of an isosceles triangle here, had two base angles of 32, then found the angle at the centre here, and halved that for the angle at the circumference and worked your way through it that way. But there's always a couple of ways to solve these questions. I think that way obviously just involved a little bit less drawing and having to sort of think outside the box. But there we go. There's a way of doing that question as well. Let's have a look at another one. Right, okay, now after this question we're going to have a look at 3 exam style questions as well, but this is our last little question on some of these, what I would say, easier type of questions. But it says PT is a tangent to the circle, and it says POS is a straight line again, so thinking about using our straight line rules as well in this question. So work out the size of the angle marked X, and you must give a reason for your answer. Now at the moment we've got this, I'm going to highlight it, we've got this right angled triangle here, and we know it's right angled because we've got a tangent meeting the radius there. So straight away I'm going to draw that right angle in, and then we can obviously work out this missing angle in the triangle here. So I'm just thinking about what I can work out without even looking at the X for the moment. Now that is just going to be angles in a triangle, so we've got the 90 and the 32 at the moment, or we could just do 90 take away 32 as there's 90 degrees left once we get rid of that right angle. So 90 take away 32 leaves us with 58 degrees. There we go, so there's our first bit of working out, we've got 58 degrees just there. Now we've got angles on a straight line, so the angle next to that we can work out straight away. So we can get this one here, and that's going to be 180 take away 58. Obviously the angle's on a straight line equaling 180, writing down those reasons. So 180 minus 58 leaves me with, let's have a look, 122 I believe. Let's just double check that, 122, yep, absolutely fine. Now this is again one of these isosceles triangles coming in, because we've got this triangle here made by these two lengths that are the radius, so that forms a little isosceles. And again we know base angles in an isosceles are equal, so we can find the size of X along with this one when we find out those base angles. So if we do 180, take away the 122, obviously again leaves us with 58. It was just the opposite way around of what we did a second ago, and then we can split that in 2, so dividing that by 2 leaves us with 29 degrees for that one. There we go, so we get 29 degrees for this question as well. There we are, so that's our answer there, 29 degrees, finishing that off, and just obviously let's just have a look at what reasons we use there. So the first reason that we had was angles made by the radius and the tangent being 90. Then we had angles in a triangle, then we had angles on a straight line, and then we had base angles in our isosceles being equal. So obviously not a huge amount of circle theorems actually going on in a lot of these questions. It's more just a one circle theorem, possibly two, and then a lot of triangles and straight lines and all those sort of normal angle rules that we're used to using. Alright, let's have a look at some exam questions. Right, okay, so a lot more language in these questions here because I've not shortened anything down. Just here it is as it would appear on an exam. So A, B and D are points on the circumference of a circle, centre 0. EDC is a tangent. BDC is 57, that's not given to us on the diagram, so let's label that. B to D to C, there we go, that's that one there, and that's 57 degrees. Find the size of angle AOB, so let's have a look. AOB is that one there. Now again, let's not worry about sort of how we get to that angle at the moment, just have a think about what we can find. Now I've spotted two things that we can find. So one thing I'm thinking about is obviously where the radius meets the tangent is 90. So I'm straight away thinking we can find this one here. So if we do 90 take away 57, that's going to give us that one. So 90 minus 57, and again our reason here is angles where the tangent meets the radius is 90. So let's take that away and we are left with 33 degrees. And there we go, we can label that in the diagram, let's get rid of that and label that in there, 33 degrees, there we go, that's just in there. Now the next thing I've also spotted is that this angle here that we've started with, given to us in the question, is the angle where that tangent meets that triangle, and that triangle there, let's have a look, does meet on all points on the circumference of the circle. So we can do our alternate segment theorem, we can go through the angle, up the line, and there we go, it makes this angle here. So if we get rid of that, we know that this angle here has to be equal to that 57 due to our alternate segment theorem. So angles in alternate segment theorems are equal. Sorry, angles in alternate segments are equal. There we go, so that must be 57 degrees. So we've got a couple of angles there. Let's have a look at what we can find now moving from this. So we've got, I'm going to highlight this, we've got that this triangle here has two lengths that are the radius, so therefore they're equal. So actually that has to be an isosceles triangle. We do actually also have that on the other side as well. So if I just highlight this, we've got the radius there, the radius there. So we've actually got another isosceles triangle here. So we could probably find our way through the triangle via that route. But actually as we've now got this 57, and we know the base angles in an isosceles are the same, this here must also be 57. So actually we've just got one angle left in an isosceles triangle, and I can always draw that out to the side if you like. You can always redraw some of these triangles. We've got 57, 57, and we're trying to find that top angle there. So if we add them together, that's 114 degrees, and we want to take that away from 180. So 180, take away 114, leaves us with 66 degrees, and that's our final answer for this question. So that's there is going to be 66 degrees. There we go, 66 degrees, final answer. But again, we could have taken some different routes here. So let's just have a quick look at this one. So if I didn't take that route, so if I get rid of a little bit of this, let's get rid of that, and forget we found those. So we're trying to find this one. Can we get there with another route? Now we had that this one was 33, and I said obviously this is another isosceles. So we've got a base angle going on down there, so that's also 33. So we could find the top angle in that triangle instead. We could add together the two 33s, that would give us 66. And take that away from 180, and that would leave us with, let's have a think, 114, there we go, and that means that if this one's 114, now we've got angles on a straight line. So angles on a straight line, you could do 180, take away the 114, which obviously again leaves us with our 66 there. So you could actually do that with just the one circle theorem. You didn't even have to use the alternate segment theorem. You could just do the tangent meets the radius at 90, and then base angles in an isosceles, and then angles on a straight line. Okay, so that's probably maybe a bit of an easier route for some people that maybe struggle with using the alternate segment theorem. You could have actually done that without it. But there we go, let's have a look at another question. Right, okay, so this question says work out the size of angle CAD. So CAD is this one here. Now we've got a few angles that are given to us. We've got angle ADE equals 54, so ADE equals 54, this one here. There we go. We've got angle ABC equals 114, so A to B to C, that's that one there, 114. There we go, and we need to try and find out this angle here. Now let's have a think about what we can find. Now we haven't got any radius meeting the tangent, so we can't do any 90 degrees, but we have got a triangle meeting that tangent, so we can apply the alternate segment theorem, and we have a cyclic quadrilateral within there, so I think we're going to be just thinking about those two circle theorems, the alternate segment theorem and the cyclic quadrilateral. Obviously those opposite angles being equal to 180. So I think that's probably the easiest one to find straight away. I can go opposite this 114, and I can do 180, take away the 114, and that leaves us with 66 degrees there for that opposite angle. So that there is 66. Let's get rid of this arrow. There we go, and we can label that 66 degrees. Now whether we'll need it or not, we can find obviously this missing angle now on the straight line. So I can add together the 54 and 66, and if we add those together, let's write that down, 54 plus 66 is 120. So my missing angle there on the straight line is going to be 60 degrees. There we go, so that's 60 degrees. And actually I've just spotted that's going to be quite a key one. And in fact, let's just write the working out down. 180 minus 120, and that's 60 degrees. There we go. So actually we can get to our final answer here straight away. We can use the alternate segment theorem. So we can go through this angle of 60, up the line, and there we go, it meets that angle there. So that's also going to be 60 degrees. There we are, so that's our final answer actually, 60 degrees. Okay, so what reasons did we use there? So we started off with opposite angles in a cyclic quadrilateral being supplementary or adding up to 180. Then we had angles on a straight line, and then we used the alternate segment theorem. And to be honest, that's probably, I don't know whether there is another route just looking at it at the moment, but that's probably the easiest route there. Only a couple of steps, and obviously just making sure you write down those reasons. Right, let's have a look at one more. Right, okay, now this is a great question actually, because you actually don't even have to use any circle theorems within this one. I mean, you can do if you like. Maybe I'll run through this in two different ways, but you can actually, I believe you can get to here with maybe only just the one circle theorem for this one. Now it says work out the size of angle CAO. Now all the other angles that are given to us in the information are on the diagram, so we don't need to draw anything in, but CAO is this angle here, and let's just highlight that. Now we do need to use one circle theorem here, and that is where the radius meets the tangent. Okay, and we can see that OA is the radius. It says this in the writing for the question there. But we've got 56 just over here. So if we take that away from 90, so 90 take away 56, and that leaves us with 34 degrees. There we go. So that's going to be 34 just here. Now once we've done that, we can actually work our way around using lots of isosceles triangles here. Okay, so if I have a look, I've got an isosceles triangle just here, where 34 is one of my base angles. So let's work that up to here, 34. And then I can actually find this angle just here at the top of that isosceles. There we go, so you can always redraw this to the side if you want. But there we go, we've got 34, 34, and we want to work out that top angle. So add those both together is 68, and if we take that away from 180, that gives us our value of the top angle there. And what's that when we take that away? Is that 112? There we go, 112 degrees. So that angle there is 112. Now it's up to you. You can actually split this up into different isosceles triangles now. I'll show you what I mean. I could actually just draw this little line in here, and I've actually just created three isosceles triangles. We've obviously got the one that I've highlighted in yellow. You've got another isosceles triangle here, and I can just repeat the process that I've just done. Or well, not all, but once you've done that, you've also then got another isosceles triangle here. And again, you can just keep repeating the process for three isosceles triangles, and you can get down to that final answer. It's a little bit slower, but there is a process that you can do with using very minimal circle theorems in this. But the next one that I've spotted, which I think is probably the best way to go about doing this if you want to do them nice and quick, is to go for this angle at the centre here, and then we've got an angle at the circumference. So that angle at the circumference there is half the size of the one at the centre. So if we do that divided by 2, 112 divided by 2, let's see, what does that give us? That gives us 56 degrees. There we go, so this one up here must be 56 degrees. Let's see if that actually helps us. I'm not sure where we're actually going with this, but let's have a look. Now we've got to get down to that angle X there. Now there's a couple of ways that you could do this. We have got, I think it might have been easier just to do all those isosceles triangles actually. There's still quite a lot of work to be done. So we've got this shape here, there we go, which is a quadrilateral, isn't it? It's got four sides, so it's a quadrilateral. Obviously angles in a quadrilateral add up to 360. So if we go about just finding this reflex angle opposite the 112 here, so we could do 360, take away the 112, and that gives us 248. There we go, so that one there is 248. And now we've got three of the four angles in the quadrilateral there. So we can actually work this one out straight away now. We can just add those all together, so 248 plus 56 plus 35. Add those all up and we'll see what's missing up to 360. So if we add those all up, what do we get? 14, 19, carry the 1, 4, 9, 10, 11, 12, 13, and 3, so 339 degrees at the moment. So if we take that away from 360, to finish that off, 360, take away 339, and that leaves us with 21 degrees. There we go. So our final answer there will be 21 degrees, and let's just highlight that. Right, there we go. Right, obviously I did mention there was another way of doing that though, so maybe we should have a look at that, because I'm not too sure whether that was the most simple way of doing this or not. It was just a way that came to me as I was going along. But let's have a look. Let's get rid of this and have a little look at how else we could have done that. So if I do split that up, as I said before, obviously we've got an isosceles triangle there, so this is a base angle also 35, so we can work out the top angle in that triangle. So thinking about this to the side, let's have a look. We've got a base angle of 35 and another one of 35, and they add up to 70, so 180 take away 70 gives us 110 for that top angle, so that's 110. There we go. Now we can work out the angle at the top of this little right angle, because those three angles around the point have to add up to 360. So if we add those two together, you've got 110, I've just got writing everywhere now, 110 add 112 is 222, and if we take that away from 360, what does that leave us with? 138, is it? 138. There we go. And then again, we've got that final isosceles triangle there, which if I draw out over here, we've got a top angle of 138. So if we take that away from 180 and split it in two, let's see what we get. So take it away from 180 is 42, and 42 divided by 2 gives us 21 in both of those base angles. There we go, so we get 21 there, and obviously 21 for that value of x that we'd already found. So different ways that you could do it, just depends on which one you prefer really, and how you actually spot it in the moment. But I'll do it, I have to be honest, with a lot of these circle theorems, you do have to just spend a little bit of time just looking at them, thinking what can you find, where can you go, and less about thinking actually just trying to get straight to that final answer, because a lot of the time, as you can see with this one, I pretty much found every single angle in sight before I actually got to that final answer. So always just try and take that approach and just think about that as you're going through some of these questions. Okay, but that's the end of the video there. I'm going to do the next video looking at algebra within circle theorems. Then I'm also going to pick out some of the hardest circle theorem questions and go over some of those. But again, the link for those will be in the description. This was just a bit of a brief overview, just running through some of the exam style questions on this topic. Okay, but hopefully that was helpful. If it was useful, please like, please comment, please subscribe, and I'll see you for the next one.